Welcome to this video lesson. In this video, we will be doing some practice questions and projectile motion questions that are launched horizontally. In this question, we get a baseball pitcher who throws a ball horizontally, and the ball falls 0.83 meters, traveling 18.4 to the home plate, and we want to determine the ball's initial horizontal speed. Let's draw out the situation. We got the ball being thrown by a pitcher, and when it travels, it's going to start horizontally and then it's going to drop. So let's say that's kind of how the trajectory looks like. And we're going to have an initial velocity in the x direction. Let's say we had a y direction, but since the question already tells us that it's thrown horizontally, we know that this component is equal to 0, and this is event 1, and this is going to be the event 2 right here, and let's just call it 2. I'm not even going to draw the ball. Let's say it starts here, and this is also going to have the same velocity in the x direction, because we're going to assume that there's no air resistance and there is no change in velocity in this direction. Nothing is slowing it down horizontally. But vertically, the speed is definitely going to increase. We're going to have some velocity here. So this is just going to equal to v1x, or we're just going to call it vx. We don't know what the value is. And v2y, and that's just going to equal to a question mark as well. Now, we know a little bit of information about this, and I'm just going to draw some guidelines here. So we're going to have a straight line like this and a straight line like this. And basically, we have a displacement, which I don't know if you folks can see this line. So actually, I'm going to draw the guidelines a little bit with a grayer color or darker color. And this is going to be the displacement from 1 to 2 in the x direction. And we have that value. It's given to us as 18.4 meters. And we also have the displacement in this direction. That's the displacement from 1 to 2 in the y direction, and that value is 0.83 meters. I'm going to choose my sign convention. I'm going to take down to be positive, and I'm going to take right to be positive. And I'm going to highlight that. My units are meters and seconds, and let's highlight this as well so that we can easily access it at all times. Acceleration here is moving downwards, and this is acceleration in the y direction is equal to 9.81. Acceleration in the x direction, we're going to make an assumption that it's 0. I'm not going to draw it out. And the change in time, that is not dependent on x or y, but we don't know what its value is. Okay, let's draw some graphs. So we are going to have position time, velocity time, and acceleration time for x and y, and I'm going to draw them really small here. For the x direction, the velocity is constant and is positive. It's moving in the right direction, and right is my positive. And therefore, it's going to have 0 acceleration, and it's going to be a straight line. Straight line, just moving in the positive direction, because in terms of my position, everything to the right of my reference point, here assuming reference point is number 1, is positive, and everything to the left is negative. For the y direction, everything below this reference point is positive and everything above is negative. So the ball starts at the very beginning and ends somewhere in the positive section, so somewhere here. In terms of velocity, it starts at a 0 velocity. It's moving in this direction, which is the positive direction, so that's going in this direction. We connect that using a straight line because we're assuming it's a constant acceleration. and the slope of this line is positive. So that's our acceleration there. And in terms of how we come up with this graph, well, initially the slope and the velocity is 0, the slope is flat, and velocity is positive, slope is positive, so it will look something like this. We have our graphs, and I will label this as x's and this as y. And let's do our assumption. So we are going to make a few assumptions. We're going to make an assumption that there is constant acceleration and that there is negligible air resistance. Okay, now let's organize the information that we have on a table. And again, you don't have to do it this way. I'm just going to zoom out a little bit here so we have a little bit more space. But I know that some students prefer this, especially when they're beginning to do these types of questions. So I'll just go with that. So we got x and y in the x direction. We only need to care about vx, especially in this case, it's only a two-stage problem. If it's a two-stage problem, you don't really need to do stages here. So we only care about the velocity in the x direction, and we care about the displacement in the x direction. The displacement value we do have, that's 18.4, but the velocity we don't have. That's what we're trying to find later in the question. In the y direction, we have v1, and that's going, and again, you don't have to write y here, especially since you've labeled it here. I'm used to it, so I'm going to do it. v1y here is 0, v2y we don't know. Displacement from 1 to 2 in the y direction is equal to 0.83. It is totally a positive value because it's traveling in the positive direction based on our reference or sign convention, sorry. Our acceleration from 1 to 2 is also constant, and that is also acting downwards. That's positive in our sign convention, so 9.81. That's the main reason why I actually took down to be positive, because a lot of the vectors are in the same direction, so it makes things a lot easier. And I'm going to erase this little section here, and this is the change in time from 1 to 2. We don't know what that is. And basically, this is the common thing between x and y, so we don't have to break it into x and y sections. If we had multiple stages, we could do 1, 2, 2, 3, and so on, but in this case, it's just stage 1 and 2. Now, let's think about what we need to find and figure out how we're going to do it. So we need to determine the ball's initial horizontal speed, and the initial horizontal speed is vx, and speed in the x direction isn't changing, so velocity 1 and velocity 2 in the x directions are all the same. And the only equation we use in the x direction is, I'll just write it out, the speed in this case from 1 to 2, this is kind of like the average, or it's a constant value, or you can write 1, 2, or just vx, is equal to the displacement divided by the time. And that's the only equation we use in the x direction. And so what information do we have here? We have the displacement already. We don't have time. So in order to find time, I need to use the y direction. So I'm going to use a different color here. Let's use pink. So in the y direction, I have this. I have the initial velocity, I have the displacement, I have the acceleration. So I can go ahead, whenever you have three pieces of information, you can find everything else. So let's do that on the side here. I'm going to take down to be positive, and I'll use my equation that I need here. I think that's going to be the displacement equation. And since I already have this sign convention here, this is one way for me to say that I'm dealing with the y direction. And I don't have to write y here anymore in every step. So the displacement is equal to the velocity 1 multiplied by the change in time plus 1/2 of the acceleration multiplied by the change in time. When plugging in the values, the displacement in that direction is positive 0.83, and that's going to equal to velocity here. Velocity 1 is 0, so that makes this whole term 0, and that's going to equal to 1/2 9.81. And again, I'm using the positive sign convention as down, so these are all positive. I don't have to put any value as negative. And the change in time is what I'm trying to find here. I'm going to rearrange for it here, and I might skip a few steps here. And sorry, this is squared, so this would be square root of 2 times 0.83 divided by 9.81. And note that this is plus or minus, but I'm only going to take the positive because the change in time cannot be negative, at least not yet. 411 dot dot dot, and the value continues, and that's going to be my change in time. So now I can just find my velocity here. My velocity here, 1 to 2. And again, I don't have to write the x. So actually, I am going to erase it and instead just write that this is my positive sign convention, and this is going to be the displacement. The displacement is 18.4. I'm going to divide that by the change in time, which I just found, and putting that in my calculator will give me 44.7299. So therefore, the velocity from 1 to 2, it's constant value, so that's same as velocity 1. In the x direction is going to equal to, I'll just write it as x, approximately 45 meters per second. And it's in horizontal direction. And notice that in this particular case, Vy is equal to 0 at the beginning, and if the velocity only has one component, that's going to be the final velocity. So in this case, the question is asking what is the initial horizontal speed. So I have to answer the question, and it's not asking for the velocity, it's just asking for the speed. So I will just say that initial speed in the x direction is 45 approximately meters per second, and that is my final answer. Let's do one other question just to show you maybe one question which is a little bit more involved and has more parts. And in this question, we got a marble which rolls off, so I should say off, a table with velocity of 1.93 meters per second horizontally. The tabletop is 0.765 meters above the floor, pretty precise. Determine how long the marble is airborne, the horizontal range, and the velocity at impact. So let's draw this situation out. We get a table. The marble kind of comes here, it moves, and then it drops here. And it's going to have an initial velocity in the x direction, which is given to us as 1.93. And note that it's going horizontally, meaning it will not have a vertical velocity in the beginning. So that's v1y is equal to 0. And it's going to go through this path. So let's draw the path. It's going to look something like this. And it's going to end up down here. And at this point, it will also have the 2x, which is not going to change. That's going to stay as 1.93. And it is going to have v2y, which we don't actually know. In terms of displacements, it is going to be displaced from 1 to 2. So this is displacement 1 to 2 in the y direction. And that value is given to us. That's 0.765. And it's also going to displace in the x direction. And that's the displacement 1 to 2 in the x direction. Fantastic. Was it going to have an acceleration? Well, not in the x direction, but it will in the y direction. So I will put that down like this. Acceleration 9.81. And that's the acceleration from 1 to 2, stage 1 to 2. And the time is going to be the same in x and y, so I'm not going to actually give it a letter there. And that said, we also need a sign convention. In this case, we can notice that almost everything in the y direction is moving downwards, and I usually like to choose my sign convention in the same direction as my displacement, so I'm going to do down, and everything that my displacement in the x direction is to the right. So I'll choose this. You don't have to. You will get the same answer if you do everything properly using the other sign convention, but I'm just going to choose this for now. Let's do our graphs of motion. So I'll do that here just to save some space for other things later. And we're going to do x's here and y's here. And we're going to do position, velocity, and acceleration. For our x direction, for the velocity, velocity is going to be constant from stage 1 to 2. Acceleration would be 0. And the displacement, taking reference to be stage 1, will be a straight line. You can see the slope of this line is constant. That means that the slope, the value of velocity is going to be constant, and slope of this is constant, meaning the acceleration, and 0, and that means acceleration is going to be 0. For the y direction, I'm going to start with the velocity. The velocity in the initially is 0, and then it speeds up in that direction. So it's going to be here, it's going to be here. Connect that using straight line. In terms of y direction, in terms of position, initially it's here. Everything in this direction is positive, so it's going to end up somewhere here. It ends up in the positive direction. So I'm going to put a dot here, 2, 1, and the slope at the beginning is flat, and then it gets steeper and steeper in the positive direction. In terms of acceleration, this is a positive slope, so this is going to be a positive value, and the slope is constant all throughout, so we get 1 and 2. And we're going to have some assumptions here, so we're going to make two big assumptions. One is that we have constant acceleration and that we have negligible air resistance. Fantastic. Let's start solving for the questions that they're asking us. I'm just going to zoom out here. And as I do this, I'm going to draw a table which has the informations in the x and y direction. So do it like this. So we'll have x, we'll have y. For x, we only care about Vx and the displacement in the x. First one, we do have the information for this one. This is 1.93. We don't have the displacement. And for y, we have v1, we have v2, we have the acceleration. From 1 to 2, we have the displacement. from 1 to 2. And we need the time from 1 to 2, which is shared between the two. Good. So velocity 1, 0 in terms of our values. Acceleration 9.81. I'm using a positive value because this is pointing down, and my sign convention is also pointing down. My displacement is pointing down from 1 to 2. That's 0.765. Velocity 2, I don't know. I'm going to put a question mark and I don't know the time. The first question asks us how long the marble is airborne, so we need to figure out how long it takes. So let's use purple for that. We need the time. I can't use the information in the x direction because basically in the x direction I need two pieces of information to find the third. I have one and I don't have the other two, so I can't do anything yet. In the y direction, I have 1, 2, 3, so I can find the rest. So I have this, this, and this. The equation that I will use based on those is displacement. Actually, I'm just gonna do my sign convention here, meaning that I'm dealing with the y direction. And I'm gonna say my displacement is going to equal, this is from 1 to 2, is going to equal to v1 times the change in time plus 1/2 of the acceleration times the change in time squared. This is going to equal to 0 because velocity in that direction is 0. The displacement is 0.765. That's going to equal to 1/2. Acceleration is 9.81. I'm using all positive values. You can see because they're all pointing downwards and they're the same as my sign convention. Delta t squared, meaning delta t is going to equal to plus or minus square root of 2 times 0.765 divided by 9.81. And on my calculator, when I do that, I will get 0.39492 dot dot dot, meaning that the change in time is approximately 0. I need how many significant figures here? Well, I got 3, 3, and 9.81 is also 3, so I'm going to go for 3, 9, and I have to round this up, and that is my first answer. For part B, let's use a different color for this. I will use blue. I need the horizontal range, so I'll do that here. I'm going to take right to be positive, meaning that I'm dealing with the x directions only, and I don't have to write x directions anymore. So I have velocity from 1 to 2 is going to equal to the displacement from 1 to 2, and that's the average velocity equation divided by the change in time from 1 to 2. I need the displacement, so I'm going to rearrange this. And I will get my velocity value is 1.93, and I found my time to be 0.39 dot dot dot. I will use the exact value, and when I multiply that out in my calculator, I get 0.762 dot dot dot. So that is, and it's asking for the range only. It's not even asking for the direction. So you just need 1 to 2. The distance there is equal to, or you can just write range is approximately 0.762. And I will box my answer. Finally, for part C of this question, let's use a different color. Let's use pink. I get C. And we need the velocity at impact. So this is a little bit the bigger part to the question. And I might need to zoom out a couple of times actually. I'm going to zoom out first here. To find the final velocity, we need like two components of velocity. We need its x direction and the y direction. We already have the x direction, that's not changing throughout this whole way. But the final velocity starts at 0 and it gets bigger and bigger as time passes. So we need to find the y component first. So to do that, I am going to use the initial information that was given to me. I'm not going to use time just because if I made a mistake here, then I'm going to make a mistake here too. But if I use these informations, I should be pretty safe. The equation that I will use will require everything that doesn't have time in it. And that equation, if I remember correctly, is v2 squared is equal to v1 squared plus 2a change in displacement. And I know that velocity 1 is 0 plus 2 times 9.81, and the displacement in that direction is 0.765. And this is v2 squared, so v2 will equal to plus or minus square root of 15 something, and v2 will end up being, in this case, positive or negative. Well, we know that it's going down, and our positive sign convention is also down, so we're going to take the positive value here, and it's going to be 3.8741 continued, and I'm going to use the exact value as I'm continuing with my solution. So initial velocity in the x direction, final velocity in the x direction is going to be same as this, so 1.93. So I am just going to shift here and try doing the question here. In the x direction, my value is in this direction, and it's 1.93. This is velocity in x, velocity 2x. And velocity 2 in the y direction, it's going down, and its value is 3.874. And my final velocity then is starting from the tail and going to the tip. This is angle theta, and this is going to be velocity 2. So velocity 2 in terms of magnitude is going to be the square root of 1.93 squared plus 3.874 squared. And again, I'm using Pythagorean theorem here. This is 4.3283. And for the angle, tan theta is going to equal to the opposite, which is 3.874. Over the adjacent, which is 1.93. When I do that on my calculator and take the inverse of tan, I will get that theta is 63.189. So to express my final answer, v2, this is the final velocity, it's going to have an approximate magnitude of, I think my final answer needs to be in 3 significant figures, so this is 4.33. Unit is meters per second, and my direction is going to be 63.5 degrees below the horizontal. And in this case, I have my magnitude and I have my direction, and I can box my final answer here. And I'm just going to zoom out just to check to see if I've answered everything. And yeah, the velocity to impact is answered, and everything looks the same. I might have made a boo-boo in terms of rounding this one when I was looking at the answer the first time, but I think this is correct. And that's it.